Hi everyone, in this video we are going to discuss about how to find the distance between the incenter and the centroid. We are going to look at two different methods. So first we are going to look at the first method. In this method we are going to see how to find the distance between the incenter and the centroid when the coordinates of the vertices of a triangle have been provided. And once the coordinates have been provided, we can easily calculate the side lengths. All we have to do is we have to use the distance formula to find the distance between the vertices, and that will give us the side lengths. I have already created videos on how to find the coordinates of the incenter, coordinates of the centroid, coordinates of the orthocenter and coordinates of the circumcenter. I have uploaded 4 separate videos. Feel free to watch those videos. And here in this first method, we are going to use the coordinates of incenter, which kind of look like this. So when we are provided with the coordinates of the vertices of a triangle, we can easily calculate the coordinates of the incenter, and similarly we can also easily calculate the coordinates of the centroid, which kind of look like this. So once we are able to calculate the coordinates of the incenter and the coordinates of the centroid, we can then use the distance formula again to find the distance between the incenter and the centroid. And so the distance is going to look like this, and that is how we can easily calculate the distance between the incenter and the centroid. So that was the first method. Now let's take a look at the second method. In the second method, let's suppose we have been provided with the side lengths of a triangle. We have not been provided with the coordinates of the vertices. So if we are given the side lengths, then how can we calculate the distance between the incenter and the centroid of this triangle? There are a couple of well-known formulae which we are going to derive in this video here, and for that we have to do a little more construction. So let me do the constructions here. I have drawn two angle bisectors. One is the bisector of the angle A and the other one is the bisector of the angle B, and the intersection of these two bisectors will be the point which is the incenter. Next, I am going to draw two medians to find the centroid. So here we have the centroid, which is the point G. Centroid is usually denoted by uppercase G and the incenter is normally denoted by uppercase I. So I am using the same convention here. So point I is the incenter and point G is the centroid. That means D is the midpoint of BC and H is the midpoint of AC. And here we have to find that distance, the distance IG, I mean the distance between the points I and G. In order to derive the formulae, we have to do just a little more construction here. I dropped a perpendicular from G onto BC and that landed at point F. I dropped another perpendicular from I onto BC which landed at point K. And finally, I dropped a perpendicular from the vertex A onto BC which landed at point E. And then I am going to position this triangle on the x-axis having B at the origin. So the x-axis and the y-axis could look kind of like this. Since we have not been provided with the vertices of the triangle, we can draw the x-axis and the y-axis as per our convenience, because in this case we are not going to determine the coordinates of incenter or the coordinates of centroid. We are just going to find the distance between the incenter and the centroid. Now with this approach, what would be the coordinates of B? Well, obviously the coordinates of B will be 0, 0 because we have positioned the triangle in such a way that B coincides with the origin. Now for the derivation, we are going to need a few properties of triangle, and I'm going to make a note of those here, and all these properties have been discussed in my previous videos in the properties and solution of triangle series. Feel free to watch those videos. I have shared the links in the description. The first one is the half perimeter or the semi perimeter. We usually denote that with a lowercase s, which is equal to half of the sum of the three side lengths. The second property that we are going to use is delta equals r times s. Now what is r? Well, r is the in radius and delta is the area of the triangle, and the same formula can be rewritten like this: r equals delta over s. The next one we are going to use is something like this, where the uppercase R is the circumradius and that is equal to the product of the three side lengths divided by 4 times the area of the triangle. And from there again we can denote it like this: delta equals A times B times C over 4 times R. Next we are going to use the formula for the in radius. R is equal to 4 times the circumradius times sine of half of A times sine of half of B times sine of half of C. And also we are going to use another property which looks like this: in radius R is equal to S minus B times tangent of half of B. And from there we can also write it like this: we can say S minus B is equal to R times cotangent of half of B. Next, we are going to use the formula for the distance of the incenter from the vertices. In this case, we are going to use the formula for BI. and bi can be written like this: 4 times the circumradius times sine of half of c times sine of half of a. And also we are going to use Heron's formula for the area of the triangle, which kind of looks like this. And from here we can say delta square is equal to s times s minus a times s minus b times s minus c. Next, we are going to write down the coordinates of the incenter in terms of the other information. Now, what would be the x coordinate of the incenter? Well, that will be the distance bk, and bk can be written as bi times cosine of half of b, because the angle ibk is half of b, so we can write it as bi times cosine of half of b. And then I'm going to substitute the value of bi, so it can be written like this. And then I'm going to multiply a quantity like this, which is essentially 1. So I can multiply by a 1 without any problem, right? And now if you carefully look at it, we are actually getting 4 times uppercase R, which is the circumradius, times sine of half of A times sine of half of C, and also we have a sine of half of B, which actually gives us the formula for the in radius. So we are going to rewrite this quantity like this, and from there we can rewrite it like this. And then in place of r times cotangent of half of b, we are going to write it as s minus b. So we have found the x coordinate of the incenter in terms of the side lengths of the triangle. And similarly, we are going to find the y coordinate of the incenter, and the y coordinate is nothing but the distance ik, and that distance can be written as bi times sine of half of b. And if we substitute the value of bi, then it can be written like this. And if you carefully look at it, this is nothing but the in radius. The formula for the in radius is exactly like that. So we are going to denote this quantity as lowercase r, and then this lowercase r can also be written as delta over s, and that is the y coordinate of the incenter. Now if you carefully look at it, the way I am trying to denote the x coordinate and the y coordinate of the incenter, I am trying to denote them in terms of the side lengths, because if we know the side lengths, we can easily calculate s minus b, and also if we know the side lengths, we can easily calculate delta as well as s. So delta over s can be easily calculated as long as we know the side lengths. And in this method, which is the method number 2 that we are discussing now, we have been provided with the side lengths of this triangle. So we should be able to calculate s minus b and delta over s easily. So let me note down the coordinates of the incenter on the side here on the right hand side. The x coordinate is s minus b and the y coordinate is delta over s. Next, we are going to try the same thing for the coordinates of the centroid. Let's take a look at two triangles here, triangle AED and triangle GFD. If you carefully look at them, AE would be parallel to GF. Since AE and GF are perpendicular on BC, so they will be parallel lines. So that means the two triangles which are formed by the two parallel lines there, the bigger triangle AED and the smaller triangle GFD, they will be similar triangles because their corresponding angles will be equal. And because they are similar triangles, we can note that the ratios of their corresponding sides will be equal. And if you carefully look at it, AD over GD, that ratio will be actually 3:1. Why? Because we know that the centroid divides the median in 2:1 ratio. That means the AG portion will be 2 times of GD. That means AD portion will be 3 times of GD. So AD is to GD can be written as 3:1. And from here, can we write it like this? We can say GF is equal to 1/3 of AE. And also let's find the value of FD. FD can also be written as 1/3 of ED. Next, we are going to find the x coordinate of the centroid, which is the distance BF. And BF can be written as BD minus FD. Now, if you think about it, what is BD? Well, D is the midpoint of BC, which is the side length A. So BD will be half of A. And what is FD? Well, FD is actually 1/3 of ED. And then in place of ED, can we write it as BD minus BE? And then again, what is BD? Well, BD is half of A. And what is BE? Well, BE can be written as AB times cosine of B. And what is AB length? Well, AB is the side length C. So we can write it as C times cosine of B. So all I have done here is in place of BD, I have noted A over 2. And in place of BE, I have noted C times cosine of B. Because the side length AB is nothing but C units. So C times cosine of B will be the BE length. Next, we are going to simplify this a little bit. The quantity can be written like this. All I have done is I have removed the parenthesis. And then I'm going to combine the first two terms. And then I'm going to replace the value of cosine of B with the formula from the cosine law. And we know from the cosine law that cosine of B can be written as C squared plus A squared minus B squared over 2CA. So in place of cosine of B, I have written the quantity C squared plus A squared minus B squared over 2CA. everything else remained as is. And here you can see that the lowercase c, the side length c, is present in the numerator as well as in the denominator, so they will cancel out each other. And then if we do the algebraic addition of these two quantities, we are going to have something like this. And that is the x coordinate of the centroid in terms of the side lengths. Similarly, we are going to find the y coordinate of the centroid. The y coordinate is obviously gf, the distance gf, that will be the y coordinate of the centroid. And we have already figured out that gf is actually equal to 1/3 of AE, and we have to find the value of AE, and for that I have a side note here. Please take a look at the note. We can say that the area of the triangle can be written as half times BC times AE, because AE is the altitude there and BC is the base. And from there we can say then AE can be written as 2 times delta over BC. And what is BC? Well, BC is actually equal to the side length A. So we can write AE as 2 times delta over A. And that's exactly what I'm going to note here on the left hand side. So in place of AE, I have used 2 times delta over A. And if we simplify this, the y coordinate will look like this. So we have found the y coordinate of the centroid in terms of the side lengths. Now that we have been able to find the coordinates of the incenter and the centroid, we should be able to use the distance formula to find the distance between them. So using distance formula, we can say that the distance between I and G, I am denoting it as Ig, which is equal to square root of x sub g minus x sub I whole square plus y sub g minus y sub I whole square. Now for the derivation, I am not going to carry the square root sign all along, so I am just going to square both sides for now, and then again later on we will take a square root and we will come back to Ig. So for now I am just going to square both sides. So we can say Ig squared can be written like this, and here I am going to plug in the values of x sub g, x sub I, y sub g and y sub I. So then it is going to look like this. Look at it carefully, make sure I haven't missed any sign or anything. And then in the next step, I am going to replace s with a plus b plus c over 2, and also I am going to take out delta from the second quantity. From the second square, I am going to take out delta. So the quantity can be written like this. And then in the next step, I am going to do a little more simplification. So the quantity would look like this. And then I am going to replace the value of 2 times s, which is equal to a plus b plus c, because s is the semi-perimeter, so 2 times s will be the perimeter. So I'm going to replace the value of 2 times s, and I'm going to simplify a little more, and the quantity will look like this. And then we have some quantities in the numerator of the first term which will cancel out each other, and then the quantity could look like this. And in the next step, in place of delta squared, I'm going to use the quantity that comes from Heron's formula. So our quantity is looking like this now. And then in the next step, I am going to replace all the s's with a plus b plus c over 2. So the quantity could look like this. And then a little more simplification, the quantity now looks like this. And finally, if we combine them together, it's going to look like this. So now we have to simplify the numerator a little bit. I am going to take each of the terms from the numerator and simplify them separately. So the first term from the numerator will be simplified, and also the second term from the numerator will be simplified. And then again we'll combine them together. Please note that there is a plus sign there. I'm talking about that plus sign. So both the quantities in the numerator having a plus sign in between. So I'm going to simplify them separately and then we'll combine them. The first quantity was like this, and let's expand the square term. Then the quantity will look like this, and then I'm going to multiply the quantity within the parenthesis by a, then by b, and then by c to expand everything, right? So once we multiply by a, we have this quantity, and then we are going to multiply by b, we get this quantity, and then we are going to multiply that by c, and we get this quantity. So the first quantity from the numerator of the previous expression kind of expands to something like this. And next, let's expand the second quantity from the numerator of the previous expression. The second quantity was like this in the numerator of the previous expression. So now I'm going to expand this, and if we expand it, we are going to get a quantity like this. And then finally, we are going to combine them, because we had a plus sign in the numerator of the previous expression. If you remember, let me go back to that screen again. Here you see in the numerator we had a plus sign, so you have to combine both the quantities, and if we combine them together, the end result will be something like this. You can try it on your notebook. The quantity will eventually simplify to something like this. And then also remember, in the previous expression we had a denominator, and the denominator was like this, 36a squared times a plus b plus c. So I have made a note of that here. So this is our Ig squared. This value is actually representing the square of the distance between the incenter and the centroid, right? So now we are going to simplify this just a little bit. You see, in all the terms in the numerator, we have 4 times a squared as a common factor. So we are going to divide the numerator and the denominator by 4 times a squared. So the numerator will look like this and the denominator will look like this. And then if we reorganize this a little bit, we can write the numerator like this. And the denominator of course can be written like this. And in the next step, we are going to take a square root on both sides because ultimately we have to find the distance between I and g. So now we have ig squared. So I am going to take a square root on both sides. So the distance between the incenter and the centroid, which is ig, is going to look like this. It will be 1/3 of this quantity. The 9 in the denominator comes out easily. It becomes 1/3 and then everything else remain as is. So this is one formula for the distance between the incenter and the centroid when we have been provided with the side lengths of a triangle. It's pretty easy to remember, and also there is a smaller version of this formula and we are going to derive that as well. So let's look at the derivation for the second formula. To derive the second formula, I am just going to take the numerator and the denominator from the expression which is inside the square root. So this is the expression that was inside the square root, and let's try to transform it into another form. So first I am going to multiply the numerator and the denominator by a positive 4. Then the expression would look like this, and then I am going to rewrite the numerator kind of like that, and the denominator would remain as is. And now if you carefully look at it, the first portion in the numerator, that is actually a plus b plus c whole cubed. So a cubed plus b cubed plus c cubed plus 3a squared b plus 3ab squared plus 3b squared c plus 3bc squared plus 3c squared a plus 3ca squared plus 6abc, that is actually a plus b plus c whole cubed. So then the numerator can be written like this. The first portion became a plus b plus c whole cubed, and from the second portion I took out a positive 5 as the common factor, and then I wrote down everything else in the parenthesis, and also I wrote down the balance of the ABC quantity, which is actually negative 32 ABC. Please take a look at it carefully to make sure everything is still alright. And then of course the denominator will remain as is. In the next step, we are going to rewrite the quantity in the second term in the numerator in a certain way. We are going to rewrite that term like this so that we can do some factoring, and then of course the denominator has no change, it will stay as is. And now we are going to do some factoring within the second term in the numerator. The numerator can be written like this. You see, we have some nice factoring happening there, and of course the denominator has no change yet. And in the next step, we are going to rewrite the second term in the numerator kind of like this, and the denominator is still the same. And then in the next step, we are going to rewrite the larger factor of the second term in a certain way to do more factoring. So we are going to rewrite the numerator like this, and then of course the denominator still has no change. And then in the next step, we are going to do some more factoring within the larger factor of the second term in the numerator. It can be written like this, and the denominator is still the same. And then in the next step, we are going to write down the second term in the numerator in a completely factored form. So the numerator would look like this, and the denominator has no change. In the next step, we are going to rewrite the factors in the second term in the numerator in a different way. We could rewrite the numerator like this, and the denominator is still the same. And in the next step, we are going to divide the numerator and the denominator by 8. So then each term in the numerator would be divided by 8, and we can rewrite that like this. And similarly, in the denominator also, we are going to divide it by 8. So the denominator would look like this. And now if you carefully look at it, a plus b plus c over 2 is nothing but s, which is the semi-perimeter. So let's try to rewrite this expression, and the expression can be written like this. And in the next step, I am going to divide each of the terms in the numerator by s. So the first term becomes s squared, and the second term becomes something like this. I have multiplied the numerator and the denominator for the second term by an extra s. So there I have noted it as s times s minus a times s minus b times s minus c, and in the denominator where it was supposed to be just a single s, I have multiplied by one more s in the denominator as well, so it became s squared. I have multiplied this extra s here, which I have highlighted in a small yellow box. That's the extra s that I have multiplied there. And what about the third portion? Well, the third portion can be written exactly like this. In the next step, we are going to simplify a little more in the second term of this expression. The first term remains as s squared, and the second term can be written like this. If you see that quantity, the quantity in the numerator in the second term, that is nothing but delta squared. That comes from the Heron's formula. So it is delta squared over s squared. So I have written it as delta over s whole squared. And then I am going to rewrite the third term slightly differently. which can be written like this. Take a careful look, make sure that it still equates to 4 times ABC over S. Now the question is why I am rewriting like this? Well, because I want to transform this expression into something which will involve the circumradius and the in radius, and of course the semi-perimeter. Now here ABC over 4 times delta is nothing but the circumradius, and delta over S is nothing but the in radius. So we can rewrite this expression like this, and it looks very small and nice, of course, right? Can be remembered very easily. And if we rewrite it like this, we can say it is equal to 5 times r squared plus s squared minus 16 times uppercase r times the lowercase r. Now what is the uppercase r? Well, that's the circumradius, which is equal to ABC over 4 delta, and lowercase r is the in radius, and lowercase s is the semi-perimeter. So finally, we have another nice formula for the distance between the incenter and the centroid, and that will look like 1/3 times the square root of 5r squared plus s squared minus 16r times r. This brings us to the end of this video. Hope everything made sense. Thank you for watching. See you in the next video.